Hey guys, welcome to my video. Here I would like to talk about a method from one of the greatest ancient mathematicians, engineer, scientist and whatnot, Archimedes. This method of Archimedes, which in itself called the method, is really an elegant one, and I believe it would be a great example of how perspectives can help us solve the unsolved. But before that, a little about Archimedes. He lived in ancient Greece. His time comes after Euclid, and he even refers to Euclid elements in his works. He lived in the city of Syracuse and is said to have a hunger for knowledge and has helped the kings in the wars. When the Romans invaded Syracuse, which by the time Archimedes have figured out the law of levers, with which he had helped develop catapults and weapons to destroy Roman ships. And we would definitely know the Archimedes principle for buoyancy of submerged bodies, which is even widely used today, and with it, the infamous Eureka story. The king had given Archimedes with the task of finding if the crown made by the goldsmith was indeed made of pure gold or it was adulterated with silver. It is said that when he figured this out with buoyancy during his bath, he jumped out and ran across the streets of Syracuse shouting Eureka. But actually, to see how he did it, will take another video to explain, so let's move on. As an engineer, I've heard of Archimedes' principle in the context of fluid statics, but what I did not know is that he was a great geometrician. The ancient Greeks were in fact curious about everything, and the curved shapes such as circles and conics intrigued them. His works on geometry were recovered from ancient writings and was published in 1897, serves to be the best compilation of his works. And the method which I want to talk about here, I came across this method when I was reading Infinite Powers by Steven Strogatz, in which he rightfully calls Archimedes the man who harnessed infinity, which also translates to he discovered integration in his quest. To emphasize this, let us look at a method which he discusses to calculate the value of pi. One thing the Greeks had figured out was that the ratio of circumference to the diameter of a circle is constant, but the value was not known. What he does is that he inscribes a polygon inside the circle and circumscribes another polygon outside the circle. So the perimeter of the polygons create an upper bound and a lower bound on the value of the circumference. And they had figured out things with straight lines better than curves. So they know how to calculate the perimeter of polygons even though it was a manual task. Here I'm just showing the formulas with sine and tan for validation. As you refine the polygons and increase the number of sides, you inch closer and closer to the value of pi. But when the number of sides increases, this would take a great deal of manual work to compute the numbers. This was actually the best known method to calculate pi, well, until Newton came along. The so called method is actually a method he came up with to calculate the area of a parabolic segment. It can be any segment. In fact, he had multiple approaches to calculate this. We will see one such approach and then move on to the actual method. The reason I want to show this is because to emphasize how he had chopped his problems into small chunks and combined them in brilliant ways to solve the actual problem, which is in fact what integration is, harnessing the infinity. So we take a parabolic segment and first construct a triangle by joining ends of the parabolic segment and a point on the parabola. The way we choose this point is by taking the line segment closing the parabola and seeing which point on the parabola has a tangent parallel to it. This way, we can continue to divide the parabolic segment in multiple steps. Here what he shows is that a single triangle in the second step of subdivision has an area which is 1/8 of the triangle from previous step. So this way, if we continue to divide the parabola into triangles, we end up with an infinite series, and this infinite sum would ideally give the area of the parabola. Computing this infinite sum with a manipulation trick, we have the area of the parabola in terms of area of the inscribed triangle. And calculating the area of triangles was known at that time as half ph. This was one method which he discusses, and now we'll actually move on to the method, which is again to calculate the area of the parabola. We'll start with the same parabolic segment. Even this method is applicable to any parabolic segment, but here I've only considered a regular segment because I'm still a beginner to this beautiful animation tool Manim, thanks to grant of 3B1B. First, let us name the line segment AC. Then we'll construct a line that is tangent to the parabola from C and a line from the other end A parallel to the axis of the parabola, which will meet at F. Same way, we also draw a line parallel to the axis of the parabola through the midpoint of the line segment D, which meets the parabola at B and the tangent line at E. This makes our parabola ABC. Now we can form triangle inscribed by the parabola by joining AB and BC, and we also extend the line BC to meet the line AF at K. Now we consider any parallel line to the axis of the parabola. Let us make such a line MO, which meets the line CK at N and parabola at P. Now if we say something about the line PO, it should and will hold for any line parallel to the axis of the parabola or any section of the parabola. Here I would like to fast forward a property which Archimedes had proved in his works, named the quadrature of the parabola. I'm not getting into proving this, but only how he uses this property to arrive at an elegant explanation. So the property is basically this. The ratio of the line MO, which is the length up to the triangle, to the length PO, which is the same line but length up to the parabola, is the same as the length AC, which is the line segment enclosing the parabola, to the length AO, which the parallel line makes from one of its vertex. This ratio can also be written in terms of CK and KN, as you can see, the triangles ACK and OCN are similar triangles. So this is what we have from quadrature of the parabola. Now in the method, what he does is that if we construct a line HK from K by extending the line CK, and by construction we choose HK as same length as CK, then we can modify this ratio relation, and if we rearrange it and write it as a product expression, we have this. So now this holds for any section of the parabola. I think until this point anyone could have done, but what he does next is probably only what Archimedes could have done. Now he sees this product relation as a fulcrum and lever relation. You see, the length of the lines MO and PO are just a measure, and hence we could consider them balancing on a lever with MO placed at a length KN, which is varying, and PO placed at a length HK, which is fixed from the center. I would like to say this is where his engineering comes into play. So this would apply to any section of the parabola, and hence if we consider every possible section of the parabola, then we could ideally say that the area of the parabola AB, parabolic segment ABC, placed at a length HK from the center of a fulcrum lever, is in balance with the area of the triangle ACF placed at some length. So now this length is tricky because in our relation, this length, which is Kn, keeps varying. So to see it better, let's transform this irregular triangle to a regular triangle with respect to the fulcrum by keeping the area and the height same and modifying the base. So with this setup, we could intuitively say that it will be in balance when we hinge it at the centroid, which is also true, as if we distribute a uniform mass over the triangle, the centroid would be its center of gravity, and hence Kn becomes Hk over 3. Now we can write the fulcrum lever balance for this setup and substitute the length relation we have to arrive at the area of the parabola relating to the area of this triangle as 1/3 of it. So now we have the area of the parabola in terms of area of a triangle, which we know how to calculate. And there is also a relation that this large triangle is 4 times the inscribed triangle, and hence we have 4/3 of in the inscribed triangle is the area of the parabolic segment, which we also proved from the previous method. Eureka! Let us dial back a bit. So he starts by choosing a section of the parabola, builds a property on it, changes the lens to see the same from a different perspective, integrates it over the parabola, and he has managed to express the area of a curved shape, such as a parabola, in terms of a straight shape whose area is known was able to calculate. That sounds incredible, to me at least. And another we need to emphasize that changing the perspectives can help us solve the unsolved. Also, to emphasize why just finding areas which are simple to us were great at that time is because that we now know integration to calculate area of the curved bodies, and algebra to write equations of curved bodies, and a graph to visualize those equations. But in those days, none of the above were there. Even the parabola is defined as a shape you get when you cut the cone in specific angle, and not as y is equal to ax square. The notion between geometry and algebra became more clearer with the works of Descartes and Fermat, which gave the analytical geometry we study at elementary level in schools. Maybe if this had happened at Syracuse, the brachistochrone problem might have been solved at ancient Greece itself. So I would like to end the video here with a quote giving same emphasis on perspectives. If you have watched this far, thank you for your time and thanks for watching.